All right. Well, hopefully this works well. The computer's being a little slow today, so we'll see how this goes. We might have to just go to the old chalkboard approach, but hopefully you remember binomial problems. The probability is the same for each thing. Once you know that probability, you also know the probability of success. You also know the probability of failure, which we call Q. Probability of success is P. And I'd say if I gave you 100 times, what would be the probability that 25 of them would happen, or more than 25 would happen? That's when we use the cumulative one. Remember that? And so that's where we can actually use those to do that. But let's say you didn't have the technology. Let's say you didn't have your calculator with you. Those binomial tables I gave you were for only one result, not a cumulative, like the normal is, right? The normal accumulates it for you. And so what we're going to do is we're going to use a normal approximation to those binomial, just in case you don't have your calculator to do the binomial CDF. Right? That was an awesome one once you guys saw that one, how easily that worked. But what if you don't have it? How are you going to do this? You're not going to sit there and do them all. If I said there's 100 of them and I want to know what's the probability of getting 50 or less, are you going to count up number 1, number 2, number 3, number 4, all the way to 50? Are you going to add those up? I sure hope not. Okay, so we're going to try and use an approximation using the normal curve. But there are some rules. In the binomial, what was n? Do you remember from binomial? Because it's the same n it was before. Number of, not successes, but number of trials. Very good. So that's number of trials. Does it say that on here or no? Not really, does it? So that was number of trials. Again, this is back when we did binomial. We're going to approximate it using the normal curve because that table has it all for us, right? That's what n is. What was p again? Probability of what? Of success. Very good. And what I'm going to do is I'm going to take what this particular section does and I'm going to take it to another level and show you how close these approximations actually are. It's kind of tricky how they do it. It makes sense to me, but we're going to see if it makes sense to you. So this n here also means number of trials, right? That's not anything different. And then what's q then? Probability of failure, right? Or some people call that 1 minus p. Does that make sense? Right? Because if you're going to be successful 40% of the time, you're going to fail 60% of it. Right? That makes sense, right? So don't be surprised if you go to college and they don't have q anymore. They just put 1 minus p in there. It's the same thing, okay? So this is probability. And again, I told you like on the other day that this is a good review of kind of what we were doing before. Assuming I can spell properly. There we go. So what we're going to say is if these, you notice these multiplications, that's what this is, n times p has to be greater than or equal to 5. So either n has to be big enough or p has to be big enough, right? To actually get bigger than or less than or greater than or equal to 5, right? Also, n and q have to be greater than or equal to 5 for this to work. What they're saying is if it's less than 5, it's so small that the normal curve can't really do it. Because remember, what happens when things get way out there on the normal curve? The probabilities are very minute, right? And that's the binomial is going to do better with that. Okay, where here the normal struggles with that, right? Once you get beyond about 3 standard deviations, that table becomes useless, right? Like on the other assignment the other day, wasn't one of your standard deviations like 5.2 or something, and then one of them was even worse, wasn't it? 11 point something, and so it was just horrible, right? But you need to know what that means too. But that's basically what they're saying here is only use this if this works. So obviously we're going to check this first every time. Does this happen? Okay, so again, either p and q have to be big enough or n has to be big enough to take care of that. Then the binomial of area x is approximately normally distributed. That's what they're saying here is if this happens, we can use it. With a mean is just n times p. And you would have already calculated that, right? Because you're going to check if it's bigger than 5, right? So you're already going to know the mean at that point, which is awesome. And the standard deviation does take a little bit more work here. You take the square root of n times p times q. Do those formulas look relatively familiar? Aren't those the formulas that I actually gave you on the last day of binomial? And apparently all the ones I gave you then, np and nq, were greater than or equal to 5. Because otherwise there's no guarantee that works. Okay? Is np and nq normally going to be bigger than or equal to 5? Yeah, either your probability of success is going to have to be really big or really small, and n very small for this to not work. All right, if you take enough samples, this will work. Okay? And so we're going to check this first, and then we're going to use this information to try and use the normal distribution. Now, is this saying anywhere on here that we're doing sample means or anything like that, like we did in the central limit theorem? That didn't come up here, did it? Okay, so our z-score, we don't have to worry about which z-score to use. We're just going to use our normal one. And here's just an idea to show you. Here it's saying, I hope your copy is better than this. Is yours a little bit better, maybe? No? No? This is saying n is only 4, np is 1, and nq is 3. So if this is where we started, is that a really good idea? Does that look normally distributed to you? A little bit, right? Not really. But you see how nq and np are not big enough, right? But what happens as we keep going? What if n was, so this one, would we use it or not? No, we wouldn't be able to use the normal distribution. How about this one? Would this one be work out for us? Well, it's looking more, but np is only 2.5. They both have to be bigger than or equal to 5. So should we use the approximation on this one? No. How about once we get down here? Now how, look at that. Look at this thing. This was okay, right? But not very good, right? This one, oh, that's close. It's getting pretty good. This one, are NP and NQ sufficient to use that approximation? Yeah, look at this thing. You think an approximation might work on that one? Are there some that aren't quite there if we're talking about area? It's a little off, right? But what you have to remember is the binomial actually uses the midpoints. And so there's going to be some above and below. Okay, so it's going to be very, very close. Now look at this one. Look at how big N and P and NQ are getting here. We're definitely going to use it here. And look at how good that is. I mean, that's right there. Again, you should be using midpoints when you do this, because that's what binomial does. You think these on the outside will cancel out any of those that are missing on the inside? It's going to get pretty darn close, isn't it? And those of you that are in calculus know the more rectangles I make, or the width, as long as the width of that rectangle keeps getting smaller and smaller, this approximation is going to get better and better, right? To that normal curve. And then basically in calculus, that turns into integration, which is a limit process, okay? So we notice that if NP and NQ are big enough, look at how close that is. It's just ridiculous. Okay, so we can actually use that. But now how? Okay, so first let's see if you can tell me if you can actually use it. So what I think would be a good idea is in each of these to figure out, well, what is N, what is P, what is Q, and of course figure out what is NP and NQ. Because we're gonna figure out we can't use this unless both of these NP and NQ are bigger than or equal to 5. They say equal to is good enough, right? They had to come up with some threshold, right? So read this one. So 37, because we're going to use this one again, so let's make sure we do this right. 37% of Americans say that they will always, or they always fly an American flag on the 4th of July. I'm a little disappointed by that number because this is actual data. I'm a little saddened by that. Only 37%. You randomly select 15 Americans and ask each if he or she always flies an American flag on the 4th of July. Now remember, only 37% said they would. So what we're going to do is, well, what's N here? How many trials? 15, right? 15 trials right there. That's how many you picked. What's P, probability of success? Yeah, 0.37, right? Because you have to write the percent as a decimal. It's 37%, which equates to 0.37. And then Q is 0.63, right? 1 minus that, right? 100% total. And so what we have to find out is, are NP and NQ sufficient here? Are we able to go ahead and use, yeah, what'd you get for NP? 5.55. Is that one? Now, if this one's no good, do we even have to do the other one? No, if this isn't, but this one's good, right? Big enough. How about NQ? Well, let's face it, if NP was big enough in this one, let's just use logic here. NQ is going to be bigger, right? And you can always find it if you want. Now, why do you suppose I would suggest you always find NP first? Well, because what if the probability of what if P and Q were switched here? I would still probably tell you to find NP first. That's just my suggestion. And it kind of got hit. It's going to give you the mean. If it works, you've already got your mean. right? And so some people do always do the smaller one first. It's up to you. You know, if the smaller one doesn't work, then you know you're done. And if it does, you know you're good, right? So we already know our mean. Seeing we can use it, see it says here, if so, find the mean and standard deviation. If not, explain why. Well, we can. Well, the mean is just right here. You gotta love that. So they're saying, what does that mean, though? Pardon the pun. You need to be able to translate what you're finding. It's great that you can find the numbers.
You select 15 Americans.
Right, based on the percentage we were told earlier, correct? And what was said there is if I went and actually went with 15 Americans and I actually found them and I asked them, on average I would get 5.5 of them that would say they do actually fly it, and that's based off of the 37% from earlier, right? And really, doesn't that make sense? They just took 15 times 37%. You see how that works? Well, of course that's going to be your average, right? But if you don't sit there and dig into that, you're going to be like, oh, I got to follow all these steps. But doesn't that make sense? That's 37% of 15. If I change the number to 20, you just find 37% of 20, right? That makes sense if you actually sit there and think about it. Now, standard deviation, according to your little rule that's a couple pages back, that takes a little bit more work. That's right here. You have to take the square root. Again, I hope you know where the square root's kind of coming from, because how do we get standard deviation? It's variance and then take the... So how would you figure out variance for this? Yeah, just take n times p times q, right? That would be variance, and then you take the square root. So it's the square root of, what's n again, 15 in this case, right? And 0.37. I don't know why I put that parenthesis first. There you go. And 0.63. And your calculators can handle that sufficiently, right? But I'm guessing we're going to have to round here because I don't think that's going to come out to a nice number. Oh, you already got it, yes. About 1.87, yep, that's what I got. Again, what that really means is 5.5 is what the mean. That's what I would expect if I did 15 people, right? If I surveyed them or asked them. What the standard deviation means is if I went 1.87 people to the right and 1.87 people to the left, I would anticipate that about 68% right in there, right? I would get 68% of the time. That's what would happen. You see, that's what standard deviations are really used for, to find those probabilities. You see that? Okay. And then once you get beyond that, well, then it starts, the probability out there itself shrinks, but you add those probabilities to what you would have, okay? So that's what we would expect, okay? And we're going to keep track of those numbers because we are going to use them again, okay, on these notes. So why don't you go ahead and tell me what you think about this one. We got 93%. So see, here's P again. P's bigger, though, this time. So why don't you go ahead and think, can you use this approximation of the normal curve or not? Okay. I'm going to guess that NP is probably going to work because it's 93% of 65. I think we're okay there, right? But basically the question is 7% of 65 enough? That's really the question. And like I said, some people always just go find the smaller one and see if it's even worthwhile doing the other one, and that's fine if you want to do it that way. I always just do NP first just because then I know I've got the mean if it works. And if, you know, it just works that way for me. That's what I'm saying. Some people do it that way because then they know if they have to do the other one. Mm-hmm. What's N? Yep, 65 trials, right? Remember, we're really talking binomial here, and we're trying to find out, can I use the normal curve to approximate it? And what's P? 0.93, which then leaves 0.07, right? And so NQ, let's face it, NQ has the greater chance of failing here, right? Of not being big enough. And so you can always do that smaller one first if you want. So 65 times 0.07, and unfortunately you get 4.55, which basically means I don't even have to find NP. Which means, it means you can't, well, it means it's not close enough to approximate it using a normal distribution. Okay, it goes back to this idea where it's not quite good enough to actually use the approximation because the areas don't cancel out well enough. Is it still possibly pretty good? Probably, but it's not good enough. That's really the question there. And so yeah, this one's not good enough. NP is plenty good, right? It's what? Yeah, like way up there, right? 60.45 or something like that. But just because that's way above 5 doesn't make this one good enough. All right? They both have to be. Otherwise, you don't get close enough, so you can't use it. Can't approximate with normal distribution. Basically, what people set up as a margin of error there, and the margin of error is way too big. It's not going to get close enough. We don't talk about margin of error until the next chapter, but they've basically set that up that you can't approximate it. So are there any questions so far? All right, this is the part that's going to get a little interesting. Here's where my calculus background and all of that helps a lot. I think I can explain it to you in a way that you can just draw yourself a picture and figure out what numbers to use. I think I'd rather you be able to do that. The binomial distribution is discrete, like this, right here on this left. Okay, when you actually did it, that's what you were finding. You were finding the area of these rectangles. Were you necessarily concerned about all these little areas in here when you were doing binomial? No. You're saying here's the chance that 4 of them happen. Here's the chance that 5 of them happen. 6 of them, 7 of them. And you just added up however many you were supposed to, right? Or you found whichever rectangle you were supposed to find. That's what we did when we did binomial. Well, now if we want to approximate it with something that's normal, that's this over this. This one over here on the right, that's not rectangles anymore. Okay? You could use a trapezoid to approximate it. We're not going to get into that. That's a calculus idea. But we have to basically fix it. Do you agree that if I say I went from here to here on this one, and I went from here to here, just adding what's about close to here, right? If I just added these rectangles and I went and added this, do you agree they're going to be the same? No. Do you agree that on both ends, you're going to miss that much here and you're going to miss that much here, correct? If you try and do the same numbers, you agree you're going to miss a lot. So you're not going to have enough, are you? And so what this says is just move it half up or half down depending on what you need. Okay? I'm going to show you examples that hopefully it'll make sense. Okay? If not, let me know. I'll find another way to show you. Okay? And it makes 100% sense to me, but I got to make sure it makes sense to you. Okay? And the first thing we're going to do is just see, can you translate it? Because why even go try a problem if you can't translate it? Okay? So what we're going to say is it's called I should have said that. It's called the correction for continuity. This is continuous. This is discrete. There's the difference. Okay? Basically, the difference is the stuff in between counts in continuous. The stuff in between, like, doesn't count for binomial. Like 4.5, you don't care. 4, 5, you do. 4.5, you don't. All right? So we're going to try and get it so that I actually get basically the correct z-score is what we're looking for. The probability of getting between 270 and 310, there's a key word here. I wish they would have worded it differently, but inclusive. What does that mean in this part? Including what? 270 and 310. Then maybe they shouldn't have used that word. Okay? Why didn't they just say greater than or equal to 270 and less than or equal to 310? Wouldn't that have been better than saying this, inclusive? That's what I would have done. But I wanted to show you, watch out for this wording, because obviously the textbook that we're kind of using here will use that same language. So saying 210 and 310 you are interested in. Well, and 270 and 310. So let's just put them somewhere on there. Here's 270, here's 310. Do we even know what the mean is yet? No, I really don't care. I just want you to be able to put them on a normal curve somewhere. And what we want is we want the stuff that's from here all the way over to there. I hope you agree that's what we want to find as a visual, right? The problem is when we use normal, we're going to be missing some stuff. Okay? So do I want 270 to be included? Yeah. So think of 270 as almost the midpoint then. If I want that included, it's the midpoint. So I have to come over here a little ways to make sure that I get all the area I need. So it's not 270 I'm going to use, but 269.5. Okay. And I also want 310 to be included, correct? If I want it to be included, it's a midpoint, so I have to go over a little bit further. because I want it included. And so I'm going to go over a little bit further and actually use 310 and a half. Okay? Because I need those parts of those rectangles. In other words, here's your 270. Here's your 310 right in the middle. Well, let me fix that. Right? 310, got that right in the middle? I want all of this stuff in here. But you see, if I make it continuous, how I'm missing that, and I'm missing that. But we do if we're going to go, basically, how do I say it? I want to add, if I'm going to approximate it properly, I do want to take into consideration the entire rectangle. Because if I don't, do you agree that this is going to be too low? The approximation will be way too low versus the binomial actual answer. Right? Because the hard part is we can go find this binomial answer exactly because we have those calculators. That's where we're at almost an advantage, which is turning into a disadvantage because you don't want to do this. Okay? But if we did binomial, we did that CDF, do you agree it would take that part and that part into consideration? And if we don't, we're going to have a problem. Well, here's 270 is the midpoint. 310 is the midpoint. And how wide are these? They're always, we'd say go from 4 to 5 to 6. They're always how wide? 1. And so how much am I missing? Half and half, which is why we go left a half and right a half, so that when we normally distribute it, we get everything we want. Okay, yes? Binomial is always the midpoints. Yep. Mm-hmm. Because again, we're doing 1 and 2 and 3 and 4, and so it always does it right at the midpoint. Mm-hmm. And that's really the problem, is how that gets up. So what we're going to do is our x values, if we, now these are the x values if we do it binomial, clear cut. Those are your x values. But the x values for normal distribution are not that. They are right, and what we're actually going to do when we do these examples, ooh, we're running out of time fast, is we're actually going to calculate the exact, and then we're going to approximate it. We're going to see how close it is. Okay? How about getting more than 157 and less than 420? So do I want 157 and 420 this time? Do I want them? No. So again, you know what I'll do? Maybe I'll go back to that other picture again. 157 and 420. Right? Is it okay if I use the same one? Is that going to confuse you? No? Okay. Again, do we even know what the mean is in this problem? No, the mean could be 10 for all we know, but I'm just using this for graphic purposes. Okay? Now in this one, if I were to do binomial, I would take the area of this rectangle right here, plus that one, plus that one, plus that one, plus that one, right? That's what you would do binomial. But if we're going to, again, that's where that CDF comes in really heavy. It would just add those up for you. Imagine how many of those you'd have to do by hand if all you had was your table. You'd have to find the answer for 157, find the answer for 158, find the answer for 159, find the answer for every single one of those all the way up to 420, and then add them up. Yeah, that'd be great, wouldn't it? Because the binomial table doesn't do that for you. And they only normally go up to 20, so okay, keep that in mind. So 157 and 420 might be a problem. All right. What I want, though, the problem is I don't really want 420. So do I want this rectangle then? If I want it to be greater than 157, do I actually want that rectangle? So I have to go over here. Do I want this rectangle? No, so which way do I have to go? In. Okay, the hardest part is figure out which way to go. You always know you're going to go a half one way or the other. So what are your actual numbers? I don't want 157, and so it's going to actually be 157 and a half, and 4, careful, 19 and a half. So really it boils down with, do you want that rectangle or not? Okay, and if you don't, then you bring it in. Okay, you go away from that number. If you do, you include it. So for this one, yes. Yep. And think of it this way. Do I want that specific rectangle for 157 or not? And in this case, do I want the 157 rectangle? No. What if I did? 156 and a half, right? Okay. So we're going from, I lost them, what were they? 157 and a half and 419 and a half. Okay. Well, the interesting thing in continuous is that and that are the same thing in continuous. Because remember what I said the other day? What if I asked you for the normal distribution at exactly 419 and a half? What's the answer? 0. So that's where it doesn't matter really in continuous. In discrete, does that make a big difference? Oh yeah, that makes a huge difference in discrete, but not in continuous. I know it's a weird concept. Why don't you try that one all on your own, no help from me, and then we'll go back to this picture again and see if you do it. The probability of getting less than 63 successes. So I'd say envision rectangle 63 somewhere and see, do you want 63 or not, and which way do you need to go? I don't know, where should I put 63 right here? And what did it say? Less than? And I know for a fact one thing I'm going to do next year is kind of give the rectangle approach when we do binomial. That'll make this a lot easier. I'll say these are the rectangles you're actually adding in the binomial. It won't make sense to them at the time, but it'll help them when we do this part. It does say less than, right? So if we were doing it binomial, these would be the only rectangles you would add up. You would add up 0. Well, 0 is probably not. You'd add up 1, 2, 3, 4, 5, 6, 7, 8, all the way up to 62, correct? Those would be the ones you would add up because you don't want 63, do you? I want it to be less than. And so what number are you going to go up to? You're not going to go up to 63. You're only going to go up to 62 and a half. But you want everything this way, right? And so you will say, I want x to be, again, less than or less than or equal to. It really doesn't matter. It's not going to change anything. What's that? You would put 0 in there because is there a possibility that it never happens? For most things. Yeah. Is it normally a very high probability? No. But I think there wasn't that hurricane one, wasn't it? Having none was it 1 and 0 were your highest. Having 5 was not a good one, right? So you have to take that into consideration. Yeah. Sure. Yeah, this will always help. If you have a different vision, you let me know because it might help others.
So is the reason you go from like 62 and a half down because like you want to, there's 60, you want to have from 63 so that it's a midpoint and it's from 63 over. So I feel like then it's the side of this here.
No. Because 63 is the midpoint of that rectangle. It goes back to the midpoint approximation theorem that we did in calculus. The student that's up here would know that. So 63 is actually right here. So I don't want this half of this right, and here's actually where 62 is. Okay, so if this is where 62 is, because that's the next midpoint over, what's that? 62 and a half. And that's basically what we're going to do here. We're going to go from 62 and a half over. Okay, because 63 would be up in this area here, just a little bit beyond it. And I don't want that, because then I get way too much. Right? It'd be a terrible approximation then, because I'd be adding all of that in as well, which I don't want. It'd be way too high. And if I just do 62, it's going to be way too, approximation would be way too small. So 62 and a half gets me very, very close. Because the amount above and below is so minute, it takes care of itself. Okay? So what would I have to put? Let's see if you can figure this out. Let me give you a picture. We'll reverse it on you. Let me give you, we'll relate it on the 63, okay? The one we just did. So here's 63. Everybody okay with that? What if I wanted, so translate this one into kind of both binomial and normal. Let me tell you, know what I mean? Tell me. So I want, if those were the rectangles, and just pretend I kept going with my rectangles, okay? I want x now to be let's do binomial first. Which ones do I actually want to add up? Binomial is kind of, whoa, wrong way. Whoa, too many. This first way of talking. Okay, and then we'll see if you can do normal, which is kind of the second way of talking about it. Whoop, well, I'm really struggling here. Okay. So binomial. Which rectangles, in other words, would I add up is the question I'm asking. Yes? Go ahead. You said it kind of the opposite way I would, but that is true. But that would be the normal that you would use. That'd be the normal approximation. What would you use for binomial? 63. So you would say for binomial, which rectangles are you adding up? So for binomial, you would say take the rectangles x that are greater than or equal to 63. Does that equal to make a difference in binomial? Yeah, it's discrete. It's discrete. It does. Is 63 counted or not? So now normal is the one that we were just given, that x has to be greater than or equal to 62.5. What the person did, they just said it the other way, but they said, you said 62.5 is less than x. It's the same thing. Okay? So x has to be greater than or equal to, so that's the normal way of saying that one. Why? Because I want this one included. I have to go over here and get it. Okay? Because remember, here's 62. Here's 63. I got to go get that. Because if I miss all of this, my approximation is going to be terrible. My approximation is going to be way too low. If I go all the way over to 62, my approximation is going to be too big, and so we find that 62.5. It's very, very close. Because it's the same amount kind of above and below, if you want to look at it that way. It evens out. Okay? Yes? Yes. Yes. Okay. I'm not sitting here telling you this is an easy concept, so keep asking the questions. Yes.
Okay, I understand that you want to include 63.
Yes.
But, like, I don't understand why you go back. Like, yes, you go backwards so you can include it, but if, like, you want more than 63, like,
Mm-hmm.
that's a little piece that's less than 63.
And that's the whole idea. Because in binomial, all of this is 63. In normal, just right there is 63. If I go a little left of that, it's 62.9. And so I need, in binomial, this is all the same. But if I start looking at this curve, here's the only one that's 63 for an x value. All these in here are less than that. And do I want all of those x values according to the normal? I do. They talk differently. Okay? There's no necessarily 62.5 in binomial. It's either 63 or it's 62. And I need to include those little pieces in the normal because they speak different languages. And that we have to translate, basically, so that the normal knows how far to go. And if we don't translate properly, we get either too much or not enough. And the approximation is terrible. Okay? There was a question? Yes. I gave you the binomial on that one. And you are to give I wanted you to translate. And we're going to run out of time, but we're going to get at least one of these examples in. And if not, I'll try and record it after school, and you can listen to it tomorrow. Okay? Approximating. Well, let's first find out, can we? All right, and how do you do that? Let's not forget. We did all that correction for continuity, but it doesn't always work, right? So how do you do that again? And then you're going to check. And let's face it, you're going to check the smaller one, right? You know, you're going to probably check that one first. So what is n? So we're back to this, but wait a minute. This is awesome. We already did this example. We already know this. It works, right? All right, so we already did this one earlier in the assignment. And so go back. I think it's example 1, isn't it? And we already know, we already checked. And I believe we already calculated these two things, didn't we? We already did that. Well, that's nice of us, huh? Or nice planning. We know the mean was what? 5.5, and we haven't talked about what that meant, right? And then we said 1.87 approximately, right, was our standard deviation. I hope that word's starting to make a little bit more sense to you, what that means, you know, if you go out that far, about how much of the time you can expect that to happen. And so what we're asking here is, what is the probability that fewer than 8 of them respond yes? Okay. What we're first going to do is we're actually going to do it using the approximation, and then I'll have you find it exactly on the calculators. Okay, we'll use that CDF. We'll see how close it is. Okay? All right. I'm looking at the wrong problem. Here we go. So what we have to do is we know it works. We can use the normal distribution. But what do we have to find in the normal distribution to actually use the table? Z-score. But the best part is of a Z-score is now you just take whatever the X value is minus the mean and divide by standard deviation. Ah, you're starting to get good at the Z-score formula. That's awesome. Right? So what X value am I concerned about here? Of all the X's that can happen, which one am I concerned about in this problem? Nope. 8. Right? I want to compare 8 to the mean, but is it actually 8? It's 8 in binomial language, but is it 8 in normal language? Why is it 7.5? Fewer. Again, you go back to that picture. Here's the binomial rectangle, right? Well, that's terrible, but you get the idea. There's 8, right? I don't want that. I don't want that rectangle. I want this stuff over here. So you use 7.5. All right, so 7.5. See, that's where the translation comes in. I got to translate the actual X value you're looking for. Minus 5.5, right? Or 5.55 divided by 1.87. Approximately, what is it? Oh yeah, 1.04. So we're within about 1 standard deviation, but it is to the right, agreed? If the mean is, and this is a terrible picture, my goodness, what am I doing? I'm going to confuse you. Why is my picture so bad? What should be right here? Yeah, I put 8 way to the left of it. That makes no sense. 5.55, 8's over here, right? Okay, sorry about that. All right, so 8's over there, but I want all this stuff. So is my percentage going to be pretty high here? Yes. Probably pretty good, right? And so you go to your little table, you find 1.04, and it's 0.8508, correct? So what's the probability? Now, does that make sense? If the mean is only 5 of them, I want 8 or less. Does that make sense that it's a pretty big probability? That's what I want you to start thinking about. If you get wrong answers that are way off, you should be like, whoa, wait a minute, how does that happen? But this is 85 point, yeah, we might as well say 0.1%, right? Now, let's go figure it out. We've got this technology. Let's do it. Why did I choose CDF and not PDF? I want to add them up. Okay, now here's the hard part. There's 15 of them, right? That's N. P was 0.37. Here was the tricky part some of you struggled with before. Is it 8? Do I want to add 8's rectangle in? No, it's only, nope, this is just binomial. You don't do halves in binomial. 7. I only want to add up that 7th rectangle. I don't want to add the 8th rectangle. Only the 7th. Was it a good approximation or not? You don't use 7.5. Is that going to be anywhere near 0.8513, the actual answer? Not even close. You use 8 or you use 8.5, not even going to be close, because that's going to throw your Z-score way off. It's going to be way too big, way too small, won't be good enough. Okay? And so that's what we're doing here. Do you want that rectangle or do you not? So in your Z-score, which language are we talking? Normal or binomial? Normal. Down here, which language are we using? Binomial. That's the key. But you see, sometimes you don't want that rectangle. I don't want the 8th, which is why it went down to 7.5, because I don't want the 8th rectangle.